Lesson 2.4 Traffic Studies Part 2. After completing this lesson, the student will be able to carry out spot speed studies using radar meter. Student will be able to present spot speed data in suitable formats, carry out travel time studies by different methods, and also the student will be able to carry out intersection delay studies. In the last lesson, we discussed about traffic volume studies, and we also started talking about the spot speed studies. There are two alternative methods that we were discussing. One is measurement of travel times as vehicles traverse a short measured distance. We talked about the possibility of error, which is called as parallax, which is a systematic error, and also we mentioned about the procedure for elimination of the systematic error. We also talked about the other kind of error which occur due to early or late pressing of the stopwatch. So, that error normally is randomly distributed, and we discussed about that also. So, in continuation to that approach for spot speed studies based on measurement of travel time as vehicles traverse a short distance, let us now understand about an equipment which is known as inoscope. In many places, inoscope is still used for measurement of spot speed, where observer start stopwatch when a vehicle crosses the entry boundary. Let us try to locate. This is one entry boundary and this is the exit boundary. So, observer is located here, and the equipment which is called inoscope is placed here. In inoscope, a mirror is placed which is shown here. The observer is standing here by the side of the road. So, as soon as the vehicle crosses this line, the stopwatch is pressed, and the moment the vehicle crosses this exit line, the image gets reflected in the mirror, and from the inoscope the observer can see that vehicle is crossing that line. So, immediately he press the stopwatch again. So, the time interval is noted, and that is the time of travelling this distance by the vehicle. Now, once you know the travel time over this short stretch, accordingly the speed may be calculated. So, let us try to summarize the steps again. Observer start stopwatch when a vehicle crosses the entry boundary. Inoscope is placed at a distance about 30 meter. So, this distance is normally 30 meter in such a way that image of the vehicle can be seen by observer when vehicle crosses exit boundary. The vehicle is crossing the exit boundary. So, that image of the vehicle gets reflected here and observer can see that. When the observer finds the vehicle, locate that vehicle at the exit boundary, the stopwatch is stopped. So, the time required for vehicle to cross the known length, which is about 30 meter, is recorded, and accordingly the speed may be calculated. Now, coming to the other procedure for measurement of spot speed, that is by using radar meters. Let us have a look. These radar meters are frequently used for measurement of spot speed. it measures speed directly by reflecting an emitted radar wave of an oncoming vehicle and measuring the difference in the frequency between the emitted and reflected radar wave. It is radar meter which is targeted to a vehicle. So, the wave, the frequency between the emitted and reflected wave, that the difference is used to calculate the speed. Now, the difference in frequency, this is normally referred to as Doppler effect. You might have studied in your schools about this Doppler effect. So, radar meter actually works based on this principle, that is Doppler effect. So, the difference in frequency is proportional to the speed of oncoming vehicle. So, that way the instrument calculates or estimates the speed. So, now there are certain aspects which are also to be discussed. There are certain practical limitations of using radar meters. So, it is an equipment which are used widely by traffic engineers, even by traffic police, but you should know the limitations or the difficulties associated with using radar meter. Let us try to understand those points. One is, it may be required to have license from the government if the waves that are generated are within the regulated frequencies and wavelength. If it is so, then in some cases, in some places, it may be required to obtain license from the government. This is a procedural aspect what one may keep in mind. Second, the accuracy of various meters may vary. To what level of accuracy the speed measurement is made, that depends on instrument to instrument. So, the accuracy may vary. So, you must check the accuracy of the radar meter what you are using, to what extent it can give correct reading. Third, a very practical difficulty, it is difficult to conceal the wave. Mostly radar guns are used, it looks like a gun, it is not a real gun, but it looks like a gun. So, you target it to the vehicle and take the reading. Now, drivers, the moment find somebody is targeting the vehicle with an instrument like that. So, they may deviate from the normal behavior. So, they may either reduce the speed or maybe they may like to stop what is happening here. So, it is necessary for all the surveys to conceal yourself and the survey team, but in this case when you are using radar meter you cannot probably do that 100%. So, it is very difficult to conceal. So, drivers tend to slow down, affecting the results of measurement. The other difficulty is accurate measurements from radar meter are obtained only when the radar wave is reflected directly along the axis of the movement. That is where or when you can really get correct reading. But in some cases it is practically difficult. Suppose a vehicle is moving, you cannot really go right in the middle of the road and then put the radar meter in the same line. So, normally the measurements are taken from the by standing by the side of the road. So, if you are standing by the side of the road and then targeting or shooting the vehicle, then the measurement is at an angle. So, it may be required to apply corrections. So, it is practically difficult and adjustment requires a good measurement of the angle of wave deflection. So, once you know this wave deflection, maybe some level of corrections one can apply. That are the two different methods. So, one is you take the measurement or you take or measure the travel time over a short stretch or use equipment like radar meters. We have understood the problems associated with both approaches. Now, we want to discuss some practical issues related to spot speed measurements, general issues, but which are practical. So, we are calling them practical issues related to spot speed measurements. Let us have a look at those points. First is, field personnel need to make an effort to conceal themselves and their activity. I am again and again highlighting these points. It is necessary, because in volume count survey also the same thing is applicable, but here it is more important to be away from the drivers. It is better if they cannot see you, because the moment you are doing some activities going on the road, or some people are gathering together by the side of the road, immediately that affects the driver behavior, and maybe the driver will slow down or do some kind of reaction to those kind of gathering, or people by the side of the road they are standing and doing something. So, it is necessary, or at least we can say that field personnel need to make an effort to conceal themselves and their activity as far as possible. Second, measurement of speed of all vehicle is practically impossible, whether you are actually measuring the travel time over a short distance, or you are using equipment like radar meter. It is practically impossible to measure speed of all the vehicles. Therefore, what is essential is that vehicles must be selected randomly without any bias. What I mean by bias? Often enumerators or survey people tend to select some category of vehicle, maybe they target fast vehicles or slow vehicles, or they may target some particular vehicle type like trucks. That kind of biasness should not be there. So, it should be truly random selections of vehicle. Don't get biased by selecting only the slow moving vehicle, or only the fast moving vehicle, or only the trucks, or only the cars, like that, because we want to get a feel of the average speed of the vehicles at that location. So, it is essential to select vehicles randomly without any bias. Third difficulty, which is again a practical difficulty, that even in light traffic platoon may forms. Obviously, if traffic is getting discharged from an intersection, you will expect that it will move in platoon, but otherwise also even in light traffic platoon may form. Maybe a truck is going or commercial vehicle is going, which is a slow moving vehicle. So, other vehicles are forced to follow that vehicle in front. So, essentially you may observe the traffic is generally light, but still queue formation is there. Now, once there is a queue, it is only the queue leader or the first vehicle that speed should be taken. We should not take the speed of the other vehicles in the platoon, because that is not their normal or natural behavior. They are able to they are forced to travel at the speed of the platoon leader. So, that cautionary thing should be there, and you must take into consideration when you are measuring spot speeds. So, measurement of speed only for the first vehicle in the platoon, and others are forced to follow the platoon leader. So, this point also should be kept in mind. Next comes how to present the spot speed data. You collect information, so you have to present it in useful formats. There are different ways spot speed data are presented. One of them is frequency table. What we do normally, once you take the speed measurements, maybe let us consider you are taking spot speed measurements using radar meter. So, normally looking at the upper and lower limit, we decide the number of groups or classes. So, what we decide, suppose maybe 25 to 100 it is varying. This is just an hypothetical example. to show you the procedure, and suppose we decided to make group based on 5 kilometer interval in speed, like 25 to 30 kilometer per hour is one group, 30 to 35, like that 35 to 40. So, the last group is maybe 95 to 100. So, we decide speed group based on certain lower limit and certain upper limit. This is not lower limit, this is actually upper limit. So, one lower limit is there, another upper limit is there. Then you decide the middle speed. Suppose in this hypothetical example, if you decide the group, one group with 25 to 30 kilometer speed, the average is maybe 27.5. Then you note down the observed frequency in group. That means, this is again not in percentage normally. So, you take what is the number of observations. That means, say maybe we observed 5 vehicles travelling in the speed range between 25 to 30. Similarly, 15 vehicles we observed in the speed range between 30 to 35, 48 vehicles we observed in the speed range between 35 to 40. So, once we fill up this column, we know the total number of vehicles that are observed during this period. Accordingly, we can calculate percentage frequency in groups. That means, 5 divided by this column total. Similarly, 15 divided by this column total, 48 divided by this column total. So, that gives us frequency for particular group, and then this gives the cumulative frequency. So, here it is 1, here it is 4, because 1 plus 3, then again 9.6 plus 4. So, cumulative frequency is 13.6 and so on. Obviously, here you get 100, because that covers all the vehicles. So, the total obviously will be 100%. Now, this is one way of presenting the spot speed data. This same information we often present in terms of frequency distribution curve, where in the x axis you plot the speed. So, it is the speed, maybe the middle value you can take or the range you can mention, and in the y axis you mention percentage frequency. That means, you take any speed group, this bar is showing how much percentage of the total vehicle are travelling with that speed range or within that group. So, you normally put it, and generally if we try to fit a theoretical curve, okay, it will look like a normal distribution curve. Look, generally it may be other distribution also, but this is normally the shape. I have just shown a typical shape, that there could be different types of distribution of speed. So, that way one can present this spot speed data, which is known as frequency distribution curve. You can also present it in terms of cumulative frequency distribution curve, where again x is the speed and y is percentage of vehicle at lower speed than x axis, because it is the cumulative frequency, and it looks like a typical shape is shown here. So, you can see how it looks like. This is the typical shape that you get for the cumulative distribution, frequency distribution curve. Now, this cumulative frequency distribution curve is very useful. You can calculate 85th percentile speed, what is normally taken as the safe speed in many cases. You can calculate the 95th or 98th percentile speed. You can also calculate the 15th percentile speed, which normally used as the lower speed limit. There are many ways this varieties of information are extracted from this cumulative distribution curve, and they are used in traffic engineering application. But this is one way of representing the spot speed data. That generally completes our discussion about the spot speed measurement. So, we have discussed different approaches for spot speed measurement, their limitations, the practical issues associated with measurements. Now, we will switch over to travel time studies. Now, travel time studies are normally carried out involving significant length of a facility or group of facilities forming a route, maybe you take a road, there could be some intersections, the road geometry may vary, the width of the road also may vary, the roadside activity may vary. So, often we need information on travel time between key points within the study area, and we use such information to identify those segments in need of improvement. Maybe along the complete route, not the complete route is having problems, maybe certain segments, certain stretches or small length or particular intersection that are problematic. So, to identify those problematic locations, we carry out travel time studies. Now, travel time studies are often coordinated with delay observations also. So, we also calculate delays at points of congestion along the study route. Maybe there is an intersection here. So, we also calculate separately the what is the delay experienced when we carried out travel time studies. So, often travel time studies are coordinated with delay observations. Now, why we carry out travel time information? I am just trying to summarize some of the uses or some of the reasons for carrying out travel time studies. Primarily to identify problem locations on facilities, as I have indicated along the route, not that the complete road is problematic, maybe there are certain locations where you have bottlenecks, where there are problems, where congestion is occurring or delay is occurring. So, we want to identify problem locations on facilities. So, if we carry out travel time and delay studies, we can identify those problem locations. To measure arterial level of service, we measure the average travel time over the segment. So, the average speed that is happening, that is operating speed. So, accordingly use that information to calculate or to see what is the present operating level of service. Then to provide inputs to traffic assignment models which focus on linked travel time. Actually, we have not discussed about this traffic assignment part, but route selection is a key issue in urban transportation, where you have alternative routes. Maybe you are traveling from point I to point Z and there are alternative routes available. So, not that everybody in an urban context use a single route. Normally, people get distributed. In uncongested situation, maybe everybody can take the shorter route. So, travel time is a key issue in doing this traffic assignment. That means, assigning the complete demand to different alternative routes, and this assignment is done normally based on the travel time on alternative routes. What are the travel times in route 1, route 2 and route 3? Accordingly, there are several assignment techniques, starting from the simplest to very complicated and sophisticated assignment techniques, and through which we distribute the traffic to different routes. So, we need the travel time information, linked travel time information, and that data also can be gathered through these studies. To provide travel time data for economic evaluation, for most of the road projects or road development projects, we need to carry out economic evaluation, and normally that is the termination point. Actually, we carry out all sorts of things, we explore different alternatives, but decision making point is economic evaluation, what is finally coming out after economic evaluation. So, there majority of the transportation projects offer some benefits in terms of travel time savings. So, we need to calculate or need to understand the travel time data and for economic evaluation. It is also necessary for developing time contour maps and other depictions of congestions in the study area. So, traffic congestion may be represented many ways. So, to develop this time contour maps and other depiction of traffic congestion, we still use this kind of studies. Now, let us come to field study techniques. Significant length of the roadway is involved. Remember that we are carrying out travel time delay study over a reasonable length of the road. It is not some 20 meter or 50 meter or 70 meter, 100 meter road. it is longer than that. So, therefore, it is very difficult to remotely observe the traffic movement on this complete study stretch, because the longer routes, there are roadside establishment. So, you may not get a suitable location where from you can record or you can observe the complete traffic movement over the stretch. So, it is difficult to remotely observe vehicle as the progress through the study section, and that is why we go for different techniques. There are three techniques which are normally used. One is floating curve technique, another is maximum cut technique, and another is average cut technique. Now, what is floating cut technique? Here we drive a test car, and the test car is asked, test car driver is asked to pass as many vehicles pass the test car. This way, test car approximates the behavior of an average vehicle in the traffic stream. Let us try to understand this part again. Through this, we are trying to find out the average travel speed representative of the traffic stream. So, what we do when the test car is moving, maybe some vehicle is trying to overtake that. So, we normally try to balance this overtaking and overtaken vehicle. Suppose 3 vehicle has overtaken the test car, and if the test car has also overtaken 3 vehicles, then these are equal, overtaking and overtaken vehicles are equal. So, we can generally assume that the test car, whatever travel time we are getting and whatever speed we are calculating based on that, that is representative of the average stream behavior. So, that may be representing the average travel time or speed of the traffic. In maximum cut technique, driver is asked to drive as fast as is safely practical in the traffic stream without ever exceeding the design speed of facility. That means, in this case, driver is asked to drive vehicle as fast as possible, keeping the safety consideration in mind and without violating the speed limit. So, he should not violate the speed limit and driving first as far as possible safely within the given condition. So, there whatever travel time you get, that travel time will give a lower range of travel time or higher range of speed that is normally expected within the given condition, but this is not the average behavior, that is representing the lower range of travel time or upper range of speed which is possible within the given situation. In average cut technique, driver is instructed to drive at the approximate average speed of traffic stream. We do not put any condition here like overtaking and overtaken vehicles, number of overtaking and overtaken vehicles are to be equal, nothing of that sort, but the driver is instructed to drive. Okay, you generally drive following that average speed of vehicles. In that process, you may overtake some vehicles, you may not, some vehicles may overtake the test car, fine. We record them, we record those numbers, but we ask the vehicle, you generally drive in an following an average speed. Remember that floating car and average car techniques, we get estimates of average travel time through the section. This gives the average stream behavior. So, average travel time through the section. Now, floating car where overtaking and overtaken vehicles are equal, that is generally applicable and suitable on 2-lane highways where passing is less and can be counted and balanced easily. because it is typically for 2-lane roads. This floating cut techniques is suitable, because the passing is less and can be counted and balanced easily. On multi-lane highways, if the test vehicle is driven using floating car technique, then it may be difficult, it may be unsafe also, because of so many vehicles, so many overtaking, opposing vehicles, all those things are there. The operation is much more complicated. So, here it may not be safe. To ask the driver, you have to overtake that many number of vehicles which have overtaken you. So, here if we try to balance the overtaking and overtaken vehicle, there may be problem and we may face unsafe condition. So, here the average car technique yields similar results with less stress experienced by the driver of the test vehicle. So, we use in such case average car technique instead of using floating car driving technique. Maximum car technique, as I have mentioned already, does not result in measurement of average condition, because maximum car technique we are asking the vehicle or the test vehicle driver to drive as fast as possible, keeping the safety condition in mind and keeping the speed limit in mind. So, therefore, it does not give average condition in the traffic stream, rather the measured travel times represent the lower range of distribution of travel times. What could be the lower range of distribution of travel time? That indication we can get by following maximum car technique. Remember that all test runs in a given study route should be with the same driving strategy, because we normally take multiple run to get a representative data, representative condition. So, all test runs should be with the same driving strategy. We should not mix up them. One, if we are following floating cut, maximum cut technique, let us follow maximum cut technique. If we are following average cut technique, let us follow average cut technique for all the test runs. So, all test runs in a given study route should be with same driving strategy. An alternative to this approaches, where roadside observers can record license plate numbers as vehicle pass designated points along the route. This is essentially an alternative technique to collect travel time. What we are doing, instead of using test car, suppose these are the different control points, we note down the registration plate number here, somebody else noting down the registration plate number here, somebody else noting down the registration number plate here, and the time also is recorded. So, afterwards matching the registration number, we can find how much time that vehicle has taken to travel this distance, how much time it has taken to travel this small stretches, like that. So, that way also we can get the travel times between the control points or designated points, and accordingly we can also calculate what is the average travel time or what is the average travel speed. This is an alternative to moving vehicle method. A little bit further discussion on floating cut technique or average cut technique. These two are almost equal. Only in one case the overtaking and overtaken vehicle are made equal, in the other case they may vary. In floating cut technique or average cut technique, speed, flow and stop delay of the stream can be obtained by noting down the followings. 1. Times at different control points. Along the route you have different control points. So, at different control points we can note down the time, location and cause of individual delay. Maybe there is an intersection here. So, in this intersection how much delay is occurring, why the delay is occurring, the location, the time and the cause, all these things can be known, can be recorded. number of overtaking and overtaken vehicles are recorded. So, what is overtaken vehicles? When the vehicle is test vehicle is moving in this direction, how many vehicles are really overtaking this stop vehicle in the same direction, that is number of overtaking vehicle, and the test car also may overtake some of the slow moving vehicles. So, they are basically we take count of those also which are overtaken vehicle. So, number of vehicles traveling in the opposite direction is also noted. Suppose we are going in this direction, some vehicles are traveling in the opposite direction, we take a count of those opposing traffic also, how many vehicles are coming from the opposite direction. So, we count number of vehicles which are overtaking, which are overtaken, and also number of vehicles which are coming from the opposite direction. For this survey or field studies, field data sheets are used which typically include the following information. I am not showing the full formats, but what are the items that are normally included in the format that I am trying to indicate. Trip number, direction of trip, because you are going and then again coming back. So, both directions and then again going, again coming back. So, we want to note down the trip number, we want to know the direction of travel, whether this way or that way, what is the journey time, what is the total stop delay, what is the number of overtaking vehicle. So, when the vehicle is traveling, say if it is north, when it is traveling towards north, what are the number of overtaking vehicle, overtaken vehicle, and vehicle coming from opposite direction. Similarly, when the test car is traveling towards south, again we note down the overtaking vehicle, overtaken vehicle, and the vehicle which are coming from opposite directions. So, all these data are recorded. From the recorded data, from multiple runs, we calculate the journey time in specified average journey time in specified direction with a flow q. How the flow is calculated? Flow is x plus y by T A plus T W. What is T A? T A is measured journey time for opposite direction. Suppose we are trying to make count flow in this direction. So, measured journey time in opposite direction means when the vehicle is traveling in this direction, that is T A. T W is measured journey time for specified direction in this direction, and x and y are, x is number of vehicles in specified direction with the test vehicle when the test vehicle was traveling in opposite direction. So, when the test vehicle was traveling in opposite directions, how many vehicles moved in the specified direction. So, we are trying to find out the flow in this direction. So, when the vehicle was moving, test vehicle was moving in opposite direction, how many vehicles were going in this direction, plus y. Y is number of vehicles overtaking the test car minus the number of overtaken vehicles by the test car. So, that they also reach to this place within this T A plus T W time. So, we add that component. Y may be positive, y may be negative, depending on the number of overtaking and overtaken vehicles. So, you calculate the flow. Now, this consider any direction of travel. Let us consider the travel time for specified direction. Now, if this is T W, we are not very sure in average car technique whether this T W represents really the average travel time. So, when we can assume that it is really representing the average travel time when the overtaking and overtaken vehicle numbers are equal. If they are equal, then this T A plus T W what is T A? T A plus T W by x plus y into y. What is y? Y is number of vehicles overtaking the test car minus the number of overtaken vehicle by the test car. So, if overtaking and overtaken vehicle in the specified direction are same, then this y value becomes 0. So, then average journey time T bar is equal to T W. If not, then we are applying some correction. Suppose more overtaking vehicles are more, or overtaking vehicle are more. Accordingly, you can understand whether the test car was really traveling at a slightly slower speed or at a slightly lesser speed than the average traffic stream, or at a slightly higher speed than the average traffic stream. So, accordingly, this correction is applied to get average journey time representative of the traffic stream from the measured journey time. And as I mentioned, if the number of overtaking and overtaken vehicles are generally equal, then this correction factor, this whole component becomes 0. So, then measured journey time for specified direction will be equal to the representative average journey time in the specified direction. Now, once you know this T value, the travel time, the length is known. So, the mean journey speed can be calculated very easily. Next is intersection delay studies. Normally, this travel time and delay studies, as I indicate, of course, we called it travel time study, but we also measure delay, but delay is en route delay at certain critical points. And when the study covers a reasonable length of the road, including the mid block locations and intersection locations. But some cases, especially for signalized intersections, it is necessary for various traffic engineering application and works to measure the delay at intersections. So, we shall also discuss this part, the measurement of delay, field measurement of delay at intersection, particularly signalized intersection. So, this comes under intersection delay studies. What we try to do here, we are essentially we try to measure the total control delay. So, what we normally measure is total control delay. Of course, in many traffic engineering studies, it may be required to measure only the stop delay, not really the control delay. But the recent developments or whatever is prescribed in highway capacity manual, we normally measure the total control delay. So, let us try to understand what is control delay. Control delay is basically time in queue delay plus time losses due to acceleration from and acceleration to ambient speed. So, a vehicle which is traveling at a normal speed, if there is no intersection, there is no other obstruction, then it would travel at its own speed. So, from that the travel time may be more or the delay may occur due to two reasons. One is the time in queue delay, when the vehicle is in the queue, that time, because the vehicle is in the queue, what is the delay that is happening? The second is there is also delay due to acceleration and deceleration of vehicle. Vehicle decelerates from the ambient speed, and also once it is cleared, it will accelerate to ambient speed. So, there are essentially two parts, both are considered in the control delay. So, control delay is defined as the time in queue delay plus time losses due to acceleration from and acceleration to ambient speed. With this background, now let us try to understand the study methodology as per highway capacity manual. So, we are only discussing the methodology that has been prescribed or that has been suggested by the highway capacity manual. Here there are two salient features. One is direct observation of vehicle in queue. So, we directly observe in the field vehicle in queue. Of course, we measure so many other quantities also, we will discuss in details. And to carry out this intersection delay studies as per highway capacity manual, we require a minimum of 2 observers. So, we shall now elaborate what these observers are expected to do, what observer 1 will do and what observer 2 will do to get a more detailed understanding about the data requirement and the process. Observer 1. Observer 1 keeps track of the end of standing queue for each cycle by observing the last vehicle in each lane that stops due to signal. Now, because of the signal, the vehicle will stop. So, observer 1 will keep track of the end of standing queue for each cycle by observing the last vehicle in each lane that stops due to signal. Here, number of vehicles in queue are recorded on the field sheet at intervals of maybe 10 seconds or 20 seconds, depending on what is the signal cycle time. Vehicle in queue counts continue beyond survey period. This is very important. You should understand this part clearly and remember it. So, vehicle in queue count continues beyond survey period until all vehicles that entered the queue during the survey period have exited the intersection. So, whatever during the survey period, whatever number of vehicles have entered, till all of them cross the intersection or exit the intersection, this vehicle in queue count will continue, because otherwise we will miss those vehicles. Now, let us see what observer 2 is expected to do. Observer 2 actually counts primarily two things. One is vehicle arriving during the survey period, total number of vehicles, how many vehicles are really arriving during the survey period. This vehicle arrival is different from vehicles which are getting discharged from an intersection. So, this fellow will count vehicles which are arriving during the survey period and also a separate count from vehicles that stop one or more times during the survey period. So, one is total how many vehicles are entering, how many vehicles are arriving, that is one count. The second count is how many vehicles are stopped, not that all vehicles which are entering will stop, all of the vehicles may not stop. So, a separate count is made for the vehicles which do stop one or more times. Now, here it is worthwhile to mention that even if a vehicle stop more than once, that vehicle will be counted only once. I repeat it, if a vehicle stops more than once, vehicle will be counted, that same vehicle will be counted only once, that it is not that how many times vehicles are stopping. What we are trying to count, how many vehicles are stopping, not how many times. So, whether it is stopping, a vehicle is stopping one time, whether a vehicle is stopping 3 times, it is a single vehicle which is stopping, that much is necessary. Now, let us take a small example to show you the further calculations. I feel that it is easy if I instead of directly giving the formulation, if it is explained with an example. So, observer 1 will typically record data like this. Of course, there will be so many other things which will be included in the field data sheets. I am not showing the detailed one, but I am only showing that an example of that. So, this is the clock time. Suppose we consider it from 6 am to 6.09 6 pm to 6:09 pm, that means for 10-minute duration. Cycle numbers are 1, 2, 3, 4 like that up to 10. So, for 10 cycles we have observed the number of vehicles in queue, and we have taken measurements at every 20-second interval. So, plus 0 second, plus 20 second, plus 40 seconds. So, you can see here the number of vehicles in queue have been recorded at 0 seconds, plus 20 seconds, plus 40 seconds for all these 10 cycles. So, here sum of all vehicle in queue counts is nothing but sum of all vehicles which are observed. Let us assume that this 0 plus 0 second total is 40, plus 20 second total is 52, plus 40 second total is 40. So, what is the sum of all vehicle in queue counts? It is 40 plus 52 plus 40, 132 vehicles. That is denoted as sum over VIQ. Let us go to the next page. Total number of vehicles during the study period, that is normally denoted as VT. This the second observer has noted, it is 120 vehicle. Total count of stopping vehicle is 75. This again has been observed by second observer. So, we are calculating average time in queue using this formulation, where IS is the time interval between time in queue counts, which is 20 seconds. You have seen that 0, 20 and 40 seconds we have taken. So, this is 20, VIQ is 132, VT is 120, and this 0.9 is an adjustment factor, empirical adjustment factor, which HCM suggests to account for errors due to sampling which tend to overestimate the delay. So, with that you calculate TQ as 19.8 seconds. There are two further adjustments are done for to account for acceleration and deceleration delay. We calculate VSLC, which is number of vehicles stopped per lane per cycle. Number of vehicles stopped per lane per cycle is total number of vehicles stopped, then divided by number of cycle and number of lanes. We have assumed here 2 lanes. So, this VLC is 3.75 vehicles. Now, FVS is fraction of vehicle stopping. This is V stop by VST, total how many vehicles stopped out of the total vehicles which arrived during that time. So, this 0.625 is calculated in this example. Now, with this we calculate the total control delay, which is TQ, the earlier delay, plus a correction factor, this component to account for acceleration deceleration part indirectly. Here FVS fraction of vehicles multiplied by CF. CF is a correction factor what may be obtained from the given table in ASTO, which is a function of basically free flow speed and vehicle stopping per lane as we calculated earlier. So, with that you can take the value of CF, multiply it with FVS and get this total control delay. That way the control delay can be calculated. A few questions. What are the practical limitations of using radar methods? Number 2, discuss different ways of presentation of spot speed data. Number 3, how the travel time studies are carried out using average cut technique. Number 4, what is total control delay at intersection? Explain your understanding about total control delay. Now, let me try to answer the questions of lesson 2.3. Discuss the personal considerations for manual traffic volume counts, design a field sheet. All personnel must be trained, training of personnel is another point. Too many observers should not clutter at one location as they may obstruct driver and cause traffic interruptions. Time must be carefully coordinated at all locations and among all counting personnels. Number of counting personnels to be decided judiciously so that they can carry out the work comfortably. You must provide some relief personals to make sure that the work goes smoothly, and work carried out by counting personnel must be supervised. These are the salient considerations. Discuss different ways of presentation of traffic data. With traffic data we present in different ways: ADT, traffic composition, hourly variation chart, turning movement diagram. This is the representation of average daily traffic, the representation of traffic composition, representation of hourly variation chart, representation of turning movement diagram. What are the different uses of spot speed data? Effectiveness of speed limits, enforcement, studying speed trend, studying the performance with respect to design application, investigating high accident locations, and etc. What are the errors normally we encounter during spot speed studies? One is this parallax, which is a systematic error and which may be removed easily. The other is basically due to early or late depressing of stopwatch. Of course, this tend to be random and expects to avoid it out with a number of observations. And also this error may be minimized, at least the percentage error is minimized by using longer trap length, but you are carrying out spot speed study. So, obviously, there is a limitation to what extent you can increase the trap length. Thank you.